So we've done the game gear now from recapping, repairing, and getting up to red light boot, which is information that's kind of available online, and you can sort of get that far with a console. After you've got to red light boot though, the next stage is completely undocumented anywhere I know. So I work on these a lot and I work on them every day. So I figured out I might as well document the processes and the things I've found while working on them. So after red light boot, and after a lot of investigation, repairing many of them and kind of proving all my assumptions, I've got to the next stage of showing you how to repair and bring up a game gear. So after the console comes out of red light boot, the next thing it wants to do is to read a game. Reading the game involves, on the 2 ASIC, which is when you've got 2 chips here, it involves both the ASICs, the MPU, which is here, and the main RAM, which talks to the MPU and the ASIC to load the game data in and process it. On a 1 chip, both of these are combined into one, so you simply have a 1 ASIC, which is called a 1 ASIC. The MPU here is also inside the 1 ASIC, so all 3 of these chips on a 1 chip become the same chip. So it only involves the 1 chip here, plus the main RAM here. If you have RAM down here, or RAM on the back here, that's the video RAM and nothing to do with this stage of the boot process. So all we care about and all we need to focus on is the chips on the rear side of the console, so it's always the chips that are on the rear, and the cartridge connector where the game loads from. So I'm going to show you now what happens in order to boot a game, and using an oscilloscope how to show and see any issue with getting the game to load. So the idea of this now is you should be able to get any console after red light boot to read and successfully boot a game. You don't need a working screen, that hasn't got a screen, well this has got a screen on but it doesn't need it. And you don't need working audio, this doesn't have audio. I can show you with a scope how to detect when a game is successfully loaded as well. So even if you have potentially a faulty screen or faulty audio, we know whether that's the case or not, and we know if the game's booted. So for this you will need an oscilloscope. We sell them on the store. I've found the best ones available at the cheapest price, or you're free to buy whichever you like. But through these tutorials I'll be using the scopes that I recommend, which is picoscopes. So let's just jump in now and take a look at a working console and see how it loads a game. Then we'll take a quick peek at a few faulty consoles and try to rapidly diagnose and fix the problems. I'll probably do the actual repairs to those in the next video. This is more about explaining how the console works when it's in a functional state. But let's just jump in and get going. So if you head over to retro6.wiki, you'll find the articles here. We have a schematics page, which gives you the schematics for the 1 and the 2 chip. So for this one, we have a 2 chip, so we download the 2 chip. And then we've already gone to recapping and red light boot, so we know how to do those. So the next stage would be pre-ASIC operation, which is just to detect that the chip is definitely running. We can detect that by looking at VSync and HSync pulses on these pins of the chip. So I'll try and remember to do that as the first check that the console's running. So that's pin 1, 2, 3, 4, 5 pins over at the bottom and the bottom corner here. And we should expect to see a VSync similar to this and a HSync similar to this, as well as a clock signal that goes to the cartridge connector. So these are an indication that the ASIC's operational, and in theory the ASIC should be functional, which means these 2 chips shouldn't be at fault. But that is not to say they are. However, if we don't see these signals, then we potentially don't have red light boot or something else has gone wrong. As long as we see this, the next step is this, which is the important part. This is reading the game cartridge. So you can read through this article after. I will glance through and explain what's going on here. So this is a screenshot of the cartridge connector, as well as all the pins that are related to it. So the main ones we're interested in is the address pins and the data pins. That's where the data gets read. We should also have the read pin, which is important, and the IO request is important to detect when the game is boot, and the reset's important to detect to make sure that the ASIC has pulled the system out of reboot. Down here is the bottom left of the 2 chip, and we have the main RAM and the MPU. And again, these are also involved in the boot, so it's the similar signals. It's the data pins, the address pins, the chip select pin, the read pin, the write pin, and that's really it. And then the IO request on the MPU. So it's similar signals. The main ones we're interested in is the address, the data, IO request, reset, and read. Going over to the ASICs themselves, again, the signals are all at the top here. So we have the address pins, the data pins, they carry on over to here with 1 at the top there. We've got some more address here, a few here, and then the I/O request and the read and write here. So mainly the top area of the two ASICs is where we focus. And then if you're on a one chip, it's much quicker and easier. There's one main RAM and one ASIC. I've also put on here the video RAM, which will be moved to the next topic when we get to it, which will be fixing any video issues and LCD issues. But for now, those are the pins we're interested in. And what we care about is these address cartridge pins. We always start at the cartridge connector, and we're looking for, the important part is, see the voltage range here, 0 to 5 volts, so between 4 and 6. And how they hit these signals here. The key to a working signal is typically that it's 5 volt signals, digital. When they're bad, so here's an example of some more. This is an example of a faulty connector. And you can see the signals are there, but they're much lower amplitude, like they're less than a volt. Sometimes they're like 3.5 volts. It can be almost full, but 3.5 volts is often faulty as well. So I'll show you what to look for. The data pins look a bit more choppy, and you just have to get used to what they look like. This is because the MPU, as well as the ASIC, as well as the RAM, and as well as the game, can all control the data lines. So they're all talking to each other and using a shared data line. The cartridge puts the actual game data on the data lines when it's asked to read the game. The main RAM, I believe, works with the MPU to partially store part of the game data as well as process it and run the code. So the main RAM also controls the data lines. I haven't confirmed whether the ASIC and the MPU actually ever control the data lines or whether they simply always read the data lines. But for so far, we can be guaranteed the main RAM and the cartridge both control the data. So this wave is a process of the ASIC holding the line high and releasing it to see if anything takes control when it's expecting data to be read. When it is, you get a signal similar to this. So you'll see that each data line looks a little bit choppy, which would normally indicate a problem, this kind of half waveform. But in the case of the Game Gear, this is normal. You'll see the signal being controlled and pulled high, and then here it's not controlled, here it is controlled. So again, it's one to look out for. This is a normal waveform where it releases control and rises and then pulls it low. So this visual waveform is normal, and this is reading again. So it's more about, I'll show you when they're faulty and kind of identify and show you when it's clear that they're faulty. We've got two faulty consoles with us, so I'm sure you'll get to see the signals. But in general, I'll talk you through this when we're scoping so you can see how the signals behave. They behave differently when a game's in versus when it's not. And then how we detect a successful game load. There are several ways. The I/O request pin only ever pulses when it thinks it's got game data. So this doesn't mean the game's successfully loaded. This could be corrupt RAM, it could be a bad game, but it's read so far into the game that it thinks it might actually have a valid game, and it starts pulsing the signal. However, an almost surefire way that I've never found not to be a valid game load is to check the sound pins, so the sound output pins, to see if you get any audio coming out of the sound pins. So with the general overview in mind, let me take you through the flow of actually scoping these pins out and seeing this behave. I'll quickly show you the schematic so you can see where these pins run, because that's also important. So we can see in the schematic here we have the cartridge connector at the top. And you can see we have the 34 volt line, the 5 volt, the write, the address lines, the data lines, and this all marries up to the image I've done here. So it's the same pins. So as we go along the cartridge connector, we're going to look for all these signals for loading the game. But you can see these address and data lines, they come down, follow this thick green line. They go all the way down, all the way across. One splits up here and goes into the, which is here, and the main RAM, which is here. So you've got these are both on the left-hand side of the console. So you can see they both have the address and data lines as well. And then if we carry on over, the address and data lines also go into the two ASICs, but they don't touch this video RAM here that's normally on the back of the console. So the things that are involved in the address and data lines, as mentioned, are the two big ASICs, which is this one, and then on the left of the console, the MPU and the main RAM. So these are the areas we need to look at, as well as the cartridge connector, to make sure that the data flows from the ASIC all the way to the RAM, all the way to the MPU, and all the way to the game cartridge. If there's a single broken line of any of the address pins, the data pins, the read pin, or the chip select pin on any one of these areas, the game won't boot. So it's important that you check every single connector and every connection is good. It's not as hard as it sounds, you just have to work through it with an oscilloscope and probe the areas. So with that said, let's now jump into the actual console and take a look at probing a working console so you can see what we're looking at. So I've got Picoscope open here. I'll do a tutorial on how to use the oscilloscope, but for now we've opened it. Click the A channel because I've got the probe connected to channel A. I check that it's in 10 times mode because my probe is a 10-to-1 probe, otherwise the voltage would be 10 times higher than it should be. And in this little box here I select plus and minus 10 volts because I want to see a 5 volt range, but I don't want 5 volt being the extreme of the window and not being able to see the ringing above and below. And that the mode's in DC. And that's all I need to do for the oscilloscope. I've then got a game gear here. I've got a clean juice, so I can just power this nice and wire-free and easy. And this is a working console, so if I just chuck Sonic in the back, we can see there we have Sega. I haven't got a contrast wheel here, so this is a little bit dicey on the setup because there's nothing to keep the screen on. But this does load a game, so if I do the boot, you can see it does load. So it's good enough, it's working, we have no audio, and we have no contrast wheel, but this console's working to be able to show you the signals that we want. So the signals we're interested in are on the back. Always start this test without a game. You don't want a game interfering with the signals at the start. You can see enough with the scope that you don't need a game in to figure out what's going on. I clip my probe on ground here. This does go through some inductors, so there is better grounds, but for the purpose of what we need to see, it's perfectly fine. So clip the scope there. Most scopes have this removable end, so you can get a nice sharp spring-loaded probe tip. And what we're going to do is probe away down. In fact, that's going to be a pain. Let me just solder a wire on. And you can do this when you're working on a board. You want to make sure you've got the flexibility to move this probe around where you want when you're probing. So I'm just going to attach this. I might as well attach this to an actual ground now as well. There we go, we have ground. So now we have that, we will connect our oscilloscope ground to the actual ground. Let's do it that way. There we go. Now we can work freely with that ground attached. Now we're in a comfortable position. If I turn on, I want to see that we have the red light boot, which you can kind of see without turning the board around if you like. There's the LED. If you cover it up so it's a bit dark, you can kind of see the red glow through the board. So because I've got studio lights in here and you can't really tell, when you're working in a regular room, you can kind of see through the board to know that it's red light boot without having to turn it over and see that there's red light boot. So the first step I mentioned was down here. What we should see, if we get the probe and touch here, is the VSync signal. And you can see it going up and down on the scope. So if I leave that on there for a minute, and I show you here, this time value here is how much time has elapsed across this gap. Because we're set up to quite fast at the minute, 10 microseconds per division, if we increase this time so it takes longer and we're seeing more, you can see now we have the VSync signal. If I set a trigger up down here to auto, to fire on channel A, when the voltage is above 1, which you can now see by this yellow symbol here, that's the level of voltage. If I keep increasing, you can see the trigger level increases. So anywhere from 1 volt and above is fine for seeing triggers. And then 50% means how far of the screen over do we want to show before and after the trigger. So this 50% is saying, show me 50% of what happened before it triggered. I don't really care about stuff that happened before the trigger in this case. I'm going to set it to like 5%. And now whenever some event happens and it goes high, we see only 5% before and everything after. And you can see here now this is a VSync signal. If we increase the time so you can see a longer distance, every one of these gaps, so every high is a new frame. So there'll be 60 of these frames per second. So if we were to increase this so we could see a full second, which would be here, so you can now see it happening, you'll have 60 of these in a second, basically, showing you what's going on. So we have a valid VSync signal. And the other signal was, I believe, 5 pins over. So go to the top, 1, 2, 3, 4, 5. And we touch here. And there you can see the H-sync signals. So if I now make the time faster, you can see those H-sync signals happen a lot more because every pulse here is per line drawn. So there's 160 of these pulses for every one of those vertical pulses, which is what we saw when we zoomed out. That's why you could see so many, because there was 160 of these per high and low on the other one. So this is showing the ASICs running and working like we want. So now if we move on to the cartridge connector and we want to take a look at these pins. The first line is sometimes 34 volts, but you don't generally want to probe that in case your oscilloscope can't handle the high voltage. The next line should be 5 volts. So if we touch on this line, you can see on the scope that it's at 5 volts. So if you bear in mind where 5 volts shows on the screen at the minute at the top right, that's your 5 volt level, because the signal's amplitude, how high up it is on the screen, does actually matter. So we know we've got 5 volts, and what we're going to be going through is these pins. So you can see I'm on pin 2 now, which is 5 volts. The next one's a right pin, which I'm not that interested in. And then it's a bunch of address lines, all the pink ones. Then it's 3 data lines, then 3 grounds, then 5 data lines. Then we have an M request, an address, a read, another pin, and then more address lines. So you tend to know these once you've done it a while by just looking. So if we go back to here now, and the idea is now to probe every one of these pins and look for the problem on screen. This is a working board, so we shouldn't see a problem. So let's see what it should look like when it's working. So you've got 5 volts here. The next pin is the right, which has got nothing. The next pin, which if I zoom in so you can see how I'm touching, you can see I'm going on the inner pad there. So there's 5. This is then the right pin, or the not right pin, which is 5 volts. The next pin should be address 12, which is showing nothing. The address 7 showing nothing. Address 6 is showing data. And you can see we've got too much data here. So I'm going to change the time division in the picoscope to be faster and faster and faster. And really, I want to look at these signals at about between 5 and 10 microseconds, which is US as a symbol. And then you get a good visual of the waveform. So if we were to make it bigger, you can see the waveform like this. So that's a good wave. That's a solid square wave, which is what we want to see. All the address lines should be solid square waves. It's only the data lines that should be anything different. So that's A6. Next one is A5. We can see valid. Also, look, because there's no game in, you'll notice the data is fairly stable. It seems to be repeating the same pattern. It's also what you will see when you insert a game as the address lines change value. So they're a lot more sporadic in how you see them. But once you've seen them, you'll understand. The next one is A4. Same thing. Next one, A3. Same thing. Next one's A2. Same thing. And you can see the data slightly different, as it should be, because each address is a different bit of the address and it's trying to load a certain address. A1, A0, and now this is where it will get interesting. D0, sorry. You can see has this kind of waveform. So it depends on the time scale. So if I do it 10 microseconds, you get this kind of wavy, which is what we said we'd expect, and you can see in the screenshots. So if we just jump to the web, and we scroll down to what we're expected to see, here is the address lines, what you'd expect to see, which is what we are seeing. Then scroll down further, and here's the data lines now. They tend to look like this, kind of a jagged waveform. They look different. When a game's inserted, you'll get data like this, and the two ASICs do have data channels that look similar to this. And you can see here, this is Sonic 2 loading on a 1 ASIC, and this is no game. I'll update this documentation to show you a screen capture of every single pin on a 2-chip and a 1-chip on all of the areas, so you can see exactly what the scope should look like. But I'll talk you through it here now, and basically that is what we want to see. So data 0 is good with no gaming. Data 1 is similar, and all the data lines on this should be similar. That's data 2, similar. Then you should have 3 ground points, so ground, 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 all expected. Now data 3, same again, just a high with a wobble in. Data 4, same again. Data 5, 6, and 7. And what you'll notice is by the time you get to 7, that's the most exaggerated pin with the most kind of noise on. So if we showed that full screen, you can see there's data pin 7, go back to 6, and you can see it's a bit less. So data pin 7 typically has the most visual little ripples, and that's completely normal. The next pin is memory request, or not memory request in this case. And you can see we have a load of pulses on that one, that's normal. We're back to an address line 10. So I'll just jump over to the web and quickly show you where we're at now. You can see we just did memory request here. We're now at address 10, and then we're going to be at the read pin, this EXM2 pin, and then a bunch of address lines, and we carry on down. So let's just carry on probing. Don't worry too much about what you're seeing. You'll get the idea as we put a game in how things look different, and when I show you a broken one, you'll understand what it looks like when it's broken. The next one is the not read. And you can see that's pulsing up and down. The next one is the EXM2 pin, which is the same. And then we're back to address lines, which would normally be pulses. So you see how address 15 isn't pulsing. That's because that's the high-end bit of the address. Similar to how address 12 and address 7 weren't pulsing anything. It's because the part of the address that wants to be read is not high enough. So these aren't expected to be high. You're never reading that high at the minute because there's no game in. Go to the next address pin, which is address 11. Then address 9, still nothing. Address 8, still nothing. And 13 and 14, nothing. Which is what is to be expected because you're only reading up to, I believe, the address bit 6 when there's no game in. So there's only the first 6 bits of the address are trying to be read, and it will never try and read higher until it reads successfully from the lower end. The next pin is the EXM1 pin, which is just high in this case. Then we should have 5 volts, which we do. And then we have the M1 pin, which is basically like a clock symbol. This next pin is important. So you see this next pin is 5 long pins from the end. This is the IO request pin. This pin only toggles when it thinks it's read some game data. So if you see toggling on this pin, it's an indication, and you don't have a game in, but this pin's toggling. That's an indication that your main RAM is taking control, and you want to look at the chip select pin might not be high. Again, all this will become clear as we diagnose and show faulty boards. The working boards will always look the same. So after IO request, there's not much of interest. The next one is a refresh pin, which is to do with the LCD timing. And then the one after is the not reset, so this should be held high. All the pins after this are just clock pins, ground pins, whether you've got an SMS game in, and TV audio, which we don't care about. So all that looks okay. You would then go and probe the main RAM, the MPU, and the ASIC for the same signals. Now, I'm not going to probe every one of these, but you can see here, for example, you've got the same data line. These pins are all data. And we know this because if we go to the web, retro6.wiki, you can see here, there's all data pins. They're the same pins that we should have seen. The address pins, the read pins. You've seen all these pins in action on the cartridge connector. So for now, I'm not going to reprobe them all because this one isn't faulty. We'll only reprobe all these when we suspect a fault. The one I would be interested in, though, is 6 pins down. So 1, 2, 3, 4, 5, 6. This pin, the chip select pin, or the not chip select pin, called not CS1, this is when this RAM chip should take over and actually output data onto the data lines. So when this pin goes low, this chip will interfere with these data lines and start controlling the data. So as mentioned, if you have no game in, because the game also controls the data line, but you see that these data pins are being controlled, then pin 6 down here is the one to look at to make sure it's held high. Otherwise it's taking control and you might have an issue here. So with that looked at and the general visual, let's get to the interesting part. Let's put a game in and see the difference now. Let's see it actually loading a game. So if we turn this on and we have a game, let's jump back into these data pins now and look how they're different. So 5 volts will be 5 volts. You can see straight away now the right pin that wasn't having any activity is now firing. This is because now the game is loading and the trigger to write to the main RAM is being fired. You go to the next pin, which is address 12, and you can see now the data is changing. So even though it's a solid up and down, notice how it's all over the place. The refresh rate and the data on screen is changing about. It's jumping all over and it's a different waveform. If I was to pause that and flick through, you can see there was one capture. There's another. There's another. There's another. You see the data's changing. It's not the same data. So that's an indication as well that the game is reading different parts of the ROM. So address 12 is now showing data. Address 7 is showing data, and all the address lines should now show data because it's reading different parts of the ROM all the time. Address 6 is reading data. 5, 4, 3, 2, 1, and 0. And now watch the data line. So this is the first data line. And now you remember this was just high with a wobble. And now look at what we've got. We have actual data being read back to us. So if we pause that and look at these scopes, you can see, in fact, if I just slow that down a bit so you can see more of it, you can see the data is being read. And this normally would indicate like faults. You'd normally see this on a scope and go, oh, there's a fault there. And some faults do look like this. So this data line's hard to tell for beginners looking at scopes, whether it's faulty or not. This kind of half here, where it's up and then half down, if it was faulty, or say you've got 2 pins joined, one pin can control the other at different times, and what would happen is you'd normally get voltage around here. You'd get a dip and it drops about halfway. If you see a halfway drop, so it had dropped about this level, and they're kind of mixed, then you might suspect a problem. But we'll see problems as we go, so you'll get used to what problems look like. But that's actually a valid data signal. It's reading data in, and the data's changing like before. So that's data 0. Data 1 is reading data. Data 2 is reading data. Then you have 3 ground points. Then you got data 3, data 4, data 5, data 6, data 7, all reading data. So this is a good game load. You've then got the memory request pin, which we're not too fussed about. You've got address 10, which should be high and low, clean signals again. You've got the read pin, which is firing. You've got the EXMP pin, which is firing. Then you're back to addresses again, which should be high, up and lows, and changing data importantly now because the data's changing. So address 15's got data, address 11, address 9, address 8, address 13, and address 14. They've all got data. You get the EXM 1 pin, which we don't really care too much about, but looks similar to address pins. The 5V pin, the M1 pin, and then this is the important one that we mentioned. This is the IO request pin. Look at that now firing on the scope. This pin I've never found to fire unless it's loaded a game, or it's at least tried to load a game, as in there is data being given back to the chip. So you can have bad cartridges where the game loads partially, you get some weird audio, you get glitching. This pin will still fire in that case because the MPU still thinks it's got some kind of data it can work with. And I think this IO request pin is the MPU down here now kicking in and processing the data and engaging the RAM. So a good sign that something's loaded is this IO request pin. If we go down to the sound pins on this chip, this is the one that I find never shows anything unless it's loaded a game successfully, because it's the game sending the audio to the console. So if we just take a look at the 2ASIC, and we're interested in the sound down here, these pins. So you have sound 1, 2, 3, and 4 that are all the initial sound channels before the mixed. And then you have sound left and sound right, which are mixed channels. You can notice they're right next to the bridged ground point. So if we go back to the scope, it should be easy to see. You can see the mixed ground pin right here. See these two pads join there? Ground, that's the good visual indicator. And it's these pins here. So this one is audio, and this one is audio. So these are the two we should see audio signals on if the game is loaded. And I can see underneath the game is loaded. So if we now probe that pin here, say for sound right, and we look at the picoscope, it's important to see the audio in the right time frame. And we've got it at 5 microseconds at the minute, US. A good visual to see audio happening is 5 milliseconds, which is MS. So if we go slower and slower and slower, come up to 5 milliseconds, you can see now you can visually see this audio. And see how it's got waves there? If I just change the voltage down to 5 volts, so it's a little larger, you can see it more. So there's the way. It's very subtle, but when you get used to audio, this is now like the rings noise playing. And you can see the audio kind of making those visual noises there. So that's the audio loading. That's almost a guarantee that the game is loaded. If I was to turn off the console, take the game out, and turn it back on, you can see we don't get any audio. So even though it looks very similar, you can see that's just static, that's just noise, nothing's happening, there's no kind of mini high and lows. Put the game back in, turn it on, and there you see that little pulse there, and then more pulses there, that's the Sega word being written out. And then there's the game loading, and the audio. So that's what audio looks like. But as mentioned, if you change the time division to being fast, so we go down to like the 5 microseconds, you're not going to visually see the audio. We can also turn off the trigger to see it much easier, because at the minute it's trying to trigger. So here's without a trigger. And we go to 5 milliseconds. You can see now it's easier to visualize. This is happening permanently and just showing everything we see. That's the audio. That's no audio. And there's audio. So there's a good way of seeing if the game's loaded by probing this audio pin. So now we've seen what the pins should look like when you probe them. There's not much to teach without showing you a problem. So I can show you the signals, with the game in, where you can see like the address 12 is signaling data. And if we slow this back down to the 5 microseconds and put the trigger back on, this is where the game loaded. If we take the game out, address 12 shouldn't have any data on because it never reads that high up. And you can see in this case, it's trying to load. So I don't think we left the console off long enough for the RAM to clear. So let's just see if this is a battery drain issue. Let's just leave the console off a minute. Let's let the voltage die, which we should be able to see by just going on the 5-volt rail. Looks like it's totally down. So we shouldn't have any voltage now. So let's just go back onto the address pin, turn on. Then you can see now we have no address. So it was just that we'd turned the console off too fast. And you can see here now a different behavior still. So there's no guarantee that the data pin's just being permanently high or a game loading. This shouldn't really be having any data interference at this point. You shouldn't really be seeing the data attempting to load on the lines. But you do note, and I have seen this in various 1 and 2 ASICs, where you will get this data showing. But the importance here to tell when it's actually valid data or not is that it's not really changing. So if we pause the scopes and go through them, you can see it's all pretty much the same symbol. It's just a bunch of waves and then one high, a bunch of waves, one high. It's not really massively changing. We go to the other data pins, you see the same kind of idea. There's just a bunch of pins and then one high. So both of these visuals are correct. When the data pins show, the same data, it's normally a sign it's okay. If the RAM was faulty and loading and gain interfered, this data would change a lot, like when there's a game in. So if we turned it on, so if we look at the data on, say, this pin here, and you can see how that looks the same. If we put Sonic in and turn on, you can see the clear difference when the game is loading actual data. So you can see the data always changing. Completely different data. So that's the difference in seeing when the data is actually loading something versus it just being, static repeating data. So that's enough of that. Let's now pull out 2 faulty boards and let's see if we can quickly diagnose them, because you're only going to learn this and understand about the game booting when you see a problem, not when you see the solution. So this is a working board. You've got a visual of how it looks. Now let's just go and see me fix a board, or 2 boards in this case, depending how quick I do them, and find the fault using a scope.